Okay, so today we're going to start looking at Chapter 5, Section 2, which is all about the sine and cosine function. So first thing we're going to talk about, you see this? This is sine. It is not any other word but sine. Do you see this? This is cosine. It's not any other word but cosine. So don't say sin and cos, or I will go crazy. Because that's not what they are. They're abbreviations for sine and cosine. Okay. So sine and cosine of a given angle theta. That's what this means. This is the argument of the trig function. So we're looking from angle theta. These are both just ratios or fractions of the sides of a right triangle. So we review what is a right triangle. It's a triangle that has a right angle. The angle theta is never the right angle. It has to be one of the other two angles. We never, when we're drawing our right triangles, we never let theta be the right angle. But anyways, we have three sides of our right triangle. We have two legs and the hypotenuse. Well, from this angle theta, the hypotenuse is always the side opposite the right angle. So if this is my right angle, this is the hypotenuse. So we're going to label that side the hypotenuse. Now the other two sides are the legs of my right triangle. You see how one leg is across from the angle theta and one leg is touching the angle theta. Does anybody remember what name we give those two sides? Opposite and adjacent. The one that is across from the angle is called the opposite leg. So we'll abbreviate that OPP for opposite. The one that is the leg that is touching the right angle is the adjacent side. So you see the way I labeled it. I would always identify the hypotenuse first because some people get confused because there are two angles that are touching theta. One of them is always the hypotenuse, therefore the other one has to be the adjacent. So if I were you, I would identify the hypotenuse first, and then you can go about identifying the opposite and the adjacent. So today we're going to focus strictly on sine and cosine of the angle theta. Sine is equal to the opposite leg over the adjacent leg. Opposite leg over the hypotenuse. Can you tell it's been a while since I've done trig? Sine is the opposite over the hypotenuse. Next, we're looking at cosine of the angle theta. Cosine is the adjacent side over the hypotenuse. Did everybody remember that? Remember that setup? Yes, no, maybe? You have some saying or some trick to remember how to know which is which. What do you remember, Moose?
It was an old hippie tripping on acid or something like
Okay, that is one of them. Okay, some old hippie caught another hippie tripping on acid is one of them that is remembered very frequently. That's what I remember. I remember Katoa. Or there used to be one that I'm sure was great back in the 1800s. Saddle our horses, canter away happily to other abodes. I mean, who in the world even uses those words anymore? But all this means, sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. We're not going to be looking at tangent today, but we will very soon. So we need to have some way to memorize this. I don't care how you do it, but you need to know sine is opposite over hypotenuse and cosine is the adjacent over the hypotenuse. Okay, let's look here at our unit circle. So quick review, what is a unit circle? It's a circle centered at the origin whose radius is 1. So you see here is my circle. radius of 1, centered at the origin. Now imagine that I can draw any radius from the center of the circle to an outside portion of the circle. So right here's the radius that they have drawn. Okay, we know this radius has a measure of 1 because all radiuses are 1. Now imagine drawing a right triangle to complete that portion of the circle. So if this is my radius, I can make a right triangle by drawing this X and this Y like so. Now if I think about the lengths here, the length along the x-axis here is just how far did I travel along the x-axis. The length of the y value here is how far did I travel up on the y-axis. So I went over, I went up, and it put me here on an outside portion of the circle. Now using our trig functions for this right triangle, we could say that sine of this angle theta is equal to the opposite. Well, what is the opposite side? It's some measurement y. We don't know what it is. We don't care what it is right now. It's any arbitrary y. Over, what is the hypotenuse? 1. So if sine of the angle theta is the opposite over the hypotenuse, y over 1 simplifies to just be y. So it turns out when dealing with the unit circle, sine of any angle theta is just the y value that's on the outside of the circle. Similarly, think through what would happen if we did cosine of the angle theta. Well, cosine would be the adjacent side over the hypotenuse. This time my adjacent side is x over the hypotenuse, which is 1. So we would say that cosine of the angle theta is just the x value of the point on the outside of the circle. So you'll see here they have labeled this point cosine of theta, sine of theta, because the x value is just the cosine of theta, and the y value is just the sine of theta. It's basically just a substitution. It's how we've gotten those points. This is going to be very important, specifically when we look at what's called our unique or special examples. So you need to know sine of theta is y, cosine of theta is x, and this is true for any point on the outside edge of a unit circle. If I were going to develop this on my own, I would teach this last, okay? But they teach it first. These are our special examples. So we're going to be asked to find sine and cosine for each of the 4 angles. Okay, so the first one, we want to find sine and cosine of 90 degrees. So I'm going to write down, okay, let's find sine of 90 and cosine of 90. So I'm thinking back to our rotations that we did last week. The positive x-axis is my initial side. If I rotate 90 degrees, that puts me up here on the positive y-axis. Now, normally, when we do these rotations, there are 4 places we can end up where we can't draw a right triangle. Like if I were to pick any point between here and here, I could make a right triangle. You see how that could happen? But what if I had a point here? Can I draw a right triangle? No, because this is my one side and there's nowhere else to draw the triangle. If my hypotenuse was here, then I could draw a triangle by going down and over. If it was here, I could go up and over. I can always draw a right triangle except for at these 4 places. That's why I call them my special examples. So if I go up to 90 degrees, well, I can't draw a right triangle from there because it's just that line. So whenever we rotate to an axis, either the x-axis or the y-axis, we have to think through our special examples, which are listed here. We have to know sine of the angle is equal to y, cosine of the angle is equal to x. So what I always do, I rotate it to an axis, so I'm going to identify what is this point on the axis. That is the point 0, 1. On the x-axis, I went nowhere. On the y-axis, I went up to 1. So I know that this point is 0, 1. Therefore, sine is just the y value. So sine of this angle is 1. Cosine of this angle is just the x value. So cosine of 90 is 0. Any questions about that? On the next rotation, it is 180 degrees. So now we are not rotating 90 degrees, we are rotating 180 degrees. So 180 degree rotation will put me here. Since I ended on an axis, I want to identify what is that point. So now on the x-axis, I went left 1, so the x value is negative 1. The y value, I didn't go up or down, so it's 0. So now if I'm identifying sine of 180, sine is just the y value. Since my y value is 0, sine of 180 degrees is 0. Now we're going to look for cosine of 180 degrees. We know cosine of an angle is just the x value. So right here, the x value is negative 1. So cosine of cosine of 180 degrees is negative 1. Questions there? Oh, no. Well, that's okay. I don't need that point anymore. Why would it swap to that eraser? Okay, now next, I'm going to rotate negative 5 pi over 2. So now we're in radians instead of degrees. So you could convert it to degrees if you wanted to. Or I know every 90 degrees is pi over 2 radians. So because it's negative, I'm going clockwise. So this will be negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2, negative 5 pi over 2. Puts me right here on the negative y-axis. So now my angle is formed here. Now I can't draw a right triangle because I'm on an axis. So I identify what are the coordinates of that point. The x value is 0. The y value is negative 1. So now if I'm finding sine of negative 5 pi over 2, sine is just the y value. So now my y value is negative 1. So sine of negative 5 pi over 2 is negative 1. If I'm asked to find cosine of negative 5 pi over 2, cosine is just the x value. So there the x value is 0. So cosine of negative 5 pi over 2 is 0. Okay, and then my last rotation is negative 4 pi. So again, because it's negative, I'm going clockwise. So this would be negative pi, negative 2 pi, negative 3 pi, negative 4 pi. So now my initial side and my terminal side are the same. So I want to know, well, what is this endpoint? Well, that is the coordinate 1, 0. So we know sine at negative 4 pi is the y value. Cosine at negative 4 pi is the x value. This is a way to help us remember what is positive in a given axis. I'm sorry, not an axis. What is positive in a given quadrant? So, again, if we think back to all we know so far, we know sine is the y value, cosine is the x value. So where are my y values positive? Well, my y values would be positive above the x-axis. Does that make sense to you? That's where my y's are positive. Where are my y's negative? That would be below the x-axis. So when I'm thinking strictly about y values, which we know y is equal to sine. My y values are positive up here. My y values are negative down here. Therefore, sine is positive in the green. Sine is negative in the red. You see where that comes from? Because sine's just the y value. Now, if you think about cosine. Cosine is what? Cosine is my x value. So think, where are my x's positive? Well, my x's would be positive when I'm shading to the right side of the y-axis. Right here is where x's are positive. Right here is where x's are negative. So a way that we use to remember that is this acronym. We say all students take calculus. All students take calculus. What does that mean? It means in the first quadrant, all of my trig functions are positive. Every one of them. All are positive. In the second one, students. Only sine is positive. Cosine is negative and tangent is negative here. Right here, take. We haven't talked about tangent yet, but this is going to be the only quadrant that tangent is positive. Tangent is the only thing positive here. Sine and cosine would be negative because, again, x values are negative, y values are negative. And then lastly, the fourth quadrant, calculus. This is the quadrant where cosine is the only positive trig function. So all of them are positive. Sine is the only one positive. Tangent is the only one positive. Cosine is the only one positive. So it says, what quadrant has sine greater than 0, cosine less than 0? So this says, where is sine positive and cosine negative? Well, sine is only positive here and here. Well, the only one that has cosine being negative is the second quadrant. So where sine is positive and cosine is negative is in the second quadrant. The next question, what quadrant has sine being less than 0 or sine being negative and cosine being negative? So where are both sine and cosine negative? That would be in the third quadrant. Right here, they're both positive. Here, sine is positive. Here, cosine is positive. This is the only one that they are both negative, would be the third quadrant. If the terminal side is in quadrant 4, which trig function is positive? So the fourth quadrant puts me here. Well, the positive trig function would be cosine. So I would say positive equals cosine. What is negative? Well, right now we're just focused on sine and cosine, so we would say sine would be negative. Tangent would also be negative there, but we're not talking about tangent yet. So the first thing we need to do is we need to look at our 45, 45, 90 special right triangle. So that's what they've drawn here. I'm going to draw my own because I don't like that that's been shaded in. It's going to be kind of hard to see. So a 45, 45, 90 special right triangle is one that has both of my angles at 45 degrees besides the right angle. Okay, and we have to memorize this triangle. Okay, so 45, 45, 90 actually has two different triangles you can memorize. The one that I first learned was radical 2, and 2. Okay, 45, 45, 90 is an isosceles right triangle. Isosceles means you have two angles that are the same. So that means we have the opposite sides also equivalent. Do y'all remember seeing this before? A 45, 45, 90? Maybe? Do you have this memorized already? No? Okay. You need to. Okay. The angles are 45. Across from the 45s are the radical 2's. Across from the 90 is a 2. Now, what we did, let me show you where the second one comes from. Because I'm just going to explain this once or twice. Because you can do all the math without knowing this. And I know most of you don't care to know where it comes from. You just want me to tell you the answer. But if you'll remember, back when you did congruence test and similarity test. So you probably don't remember the similarity test, but you probably remember the congruent test. How can I prove two right triangles? How can I prove two triangles are congruent? You know what congruent means? Same. That means they have the same angles, measures, and they have the same side lengths. So we learned a bunch of different ways to tell two triangles were congruent. At least I think you probably did, unless you got COVIDed out. But I don't think this would have been at the end. We could prove by side, angle, side. The two
Angle,
Oh,
side.
yeah, I remember that thing.
angle, angle, side.
Side angle,
No. Angle, angle, side, that's the same thing. Side, angle, angle is the same thing as angle, angle, side.
I forgot.
Side, side, side. If it was a right triangle, you could use the HL theorem, hypotenuse and a leg, to prove that they were. You remember all that? Now that's not the part that I'm going to focus on, but before you learned about congruency, you were supposed to learn about similarity. So congruent triangles have the same side lengths and the same angle measurements. Similar triangles, they have same angle measures,
They can be different sizes.
but their side lengths are different. But their side lengths have to be proportional. You know what I mean? If something is proportional, like think back to a recipe. If I was supposed to put in 2 cups of cornmeal and 2 eggs, what if I only wanted to put in 1 cup of cornmeal? Then how many eggs do I need to put in? 1, because I'm proportioning down. I'm making it by the same length. So what I'm getting to is, I can find another triangle that is proportional to this one. Because really the triangles that we're dealing with are all a hypotenuse of 1. Because everything we're dealing with is in a unit circle. Now this is going to work the same for us, I'll show you why, but in reality we're going to be using a different triangle. But this is the one that I memorized, if that makes any sense to you. Because the other one's a lot uglier. So what could we do to get the actual triangle? Well, we want the hypotenuse not to be 2, but we want it to be 1. So I divided by 2. So what would I need to do here to this one? I need to divide it by 2. And what would I need to do here? I would need to divide this by 2. So in reality, the right triangle we're using is this one. But it is proportional with this side. So what does that mean? Well, watch this. If I go sine of 45, that is the opposite over the hypotenuse. So that would give me radical 2 over 2. Looking at this triangle, which is the one I'm actually dealing with. If I did sine of 45, this would be the opposite. This would be the hypotenuse. What do I get in the end? I get the same proportion no matter which triangle I use, because I'm working with a similar triangle. Does that make sense to you? So you won't hear me explain this ever again. This is just how it works. But this is the triangle that I'm going to use, even though that's what I'm really working with.
Why did you divide it by, why did you get one with your hypotenuse?
Because it's a unit circle. has a center at the origin and a radius of 1. So if the radius is 1, the hypotenuse has to be 1. Because the hypotenuse is the radius. Okay, so now we're going to use this special right triangle in a bunch of different situations. Okay, so now we're going to be given different trig functions and we have to identify their value. So when you take this test with this part, you can't use your calculator. So you have to make sure you know how to find these values without plugging them straight into your calculator. When you're doing the homework, I'm good with checking your work with your calculator, but you better know how to do it without the calculator too. So right here first, we've got to find sine of 45 degrees. So this is our process. If I'm looking for sine of 45 degrees, I'm going to draw my coordinate plane. Now a 45-degree rotation puts me in the first quadrant. So I'm going to draw my right triangle there. Okay, so if I rotated 45 degrees from here to here, then I know that the angle, the interior angle, is 45 degrees. Is everybody with me? Because that was my rotation. Now, this is one of my special right triangles. It's a 45, 45, 90. You got to have it memorized. In a 45, 45, 90, the legs have a value of radical 2. The hypotenuse has a value of 2. Even though I'm really working with the other triangle, this one works the same. Now, for sine, sine is the opposite over the hypotenuse. So I know the opposite side is radical 2. The hypotenuse is 2. So sine of 45 is radical 2 over 2. Now, one more thing we have to check, okay, is what quadrant I'm in. I am in the first quadrant. In the first quadrant, all trig functions are positive. So because they're all positive here, then I know my answer is positive. So we're putting together everything that we've talked about into one process here. We're finding sine of 45. So sine of 45 degrees is radical 2 over 2. Now the next one, cosine of 45. So that's actually the exact same rotation, so there's no need for me to draw another triangle. I've rotated 45 degrees, and I've got the same special right triangle. It's a 45, 45, 90. Now the difference is cosine is the adjacent over the hypotenuse. Well, for a 45, 45, 90, the adjacent side is also radical 2 over the hypotenuse, which is 2. So cosine of 45 is going to be radical 2 over 2. And I am in the first quadrant. In the first quadrant, all trig functions are positive. So cosine would be positive. Any questions so far? Okay, the next one tells me to find sine of negative pi over 4. Okay, so because it's a negative angle, I'm rotating clockwise. I'm going to be rotating in this direction. Negative pi over 4, you're either going to have to convert it to degrees, or this is one of them that you need to have memorized, if you remember that whole big list we put. Pi over 4 is the same thing as 45 degrees. So this is a negative 45 degree rotation, which is going to put me here in the fourth quadrant. This is a rotation of negative 45 degrees. So now what I'm going to do is I'm going to make a right triangle out of this. Now, We haven't talked about reference angles yet. So I really don't like that we're kind of doing this out of order. That's what I was looking for just a second ago. But I think you get the same idea. So I rotated negative 45 degrees, but the angle of this triangle is 45 degrees. Negative just really told me the direction. But my reference angle when I'm doing these triangles will always be positive. We never have a negative reference angle when we're making our triangles. So now if I've rotated 45 degrees, I know I've got a 45, 45, 90. Across from the 45 is radical 2. Beside the 45 is radical 2, and the hypotenuse is 2. Now if you want to, you can go ahead and say all students take calculus. Because I'm in the fourth quadrant, only cosine is positive. I'm trying to find sine, therefore I know that this is going to be negative. And then 45 degrees, sine is the opposite over the hypotenuse. So the opposite side is radical 2. The hypotenuse is 2. So sine of negative pi over 4 is negative radical 2 over 2. Questions there? Next one, cosine of negative 7 pi over 4. So again, it's a negative rotation, so I'm thinking about rotating clockwise. This would be negative pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, negative 5 pi over 4, negative 6 pi over 4, negative 7 pi over 4. You can think about it, it's almost negative 2 pi, right? So it's almost all the way back around, but it's not quite. We're just short of that. So the terminal side is actually going to be in the first quadrant. Let me use a different color besides black. Okay, so I'm going to go ahead and form my right triangle. Now, here's one that's a little bit different that I really wish we had talked about. The different kinds of angles. Why can't I think of the reference angle? This is where I wish we'd have already talked about reference angles, but we haven't. So if you think about it, I've rotated. We know pi over 4 is 45 degrees. So from here, I've rotated down 45 degrees, which means the angle left is also 45 degrees because the entire thing makes up 90. So it's pretty easy right now because everything we're doing is 45, 45, 90, but we're fixing to do a different triangle. You got to make sure you can think through this. So since I rotated 45 degrees here, then to rotate the rest of the way down is going to be 45 degrees. Now because it's a 45, 45, 90, I know that the opposite side is radical 2. I know the adjacent side is radical 2. The hypotenuse is 2. Now I'm in the first quadrant. All trig functions are positive in the first quadrant, so my answer is positive. Cosine is the adjacent over the hypotenuse. So my adjacent side is radical 2. My hypotenuse is 2. So cosine of negative 7 pi over 4 is radical 2 over 2. Okay, then the last one here, sine of 15 pi over 4. So if I was working that, I know 16 pi over 4 is 4 pi. So it's almost 4 pi, but it's one short of 4 pi, which puts me here. It's how I would do it. Or if you want to count all the way through, 1 pi, 2 pi, 3 pi, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, 13 pi over 4, 14 pi over 4, 15 pi over 4. Or you could convert it to degrees. Again, there's no one correct way to do it. However you can figure it out, we'll take it. Okay, so I'm going to make a right triangle. Now again, my rotation, I rotated from here to here, was an extra 45 degrees, which means my interior angle is 45 degrees. This is a 45, 45, 90. Opposite to 45 is a radical 2. The adjacent side is a radical 2. The hypotenuse is 2. Because I'm in the fourth quadrant, only cosine is positive. Because I'm finding sine, I know my answer is negative. Sine is the opposite over the hypotenuse. So my opposite side is radical 2. My hypotenuse is positive 2. So that would be negative radical 2 over 2. Depending on what my central angle is, this 30 and 60 can swap places. Sometimes the 30 can be your central angle, sometimes the 60 will be your central angle. Okay, it just depends on how much you've rotated. We'll look at that. So don't think that the 30 is always up here and the 60 is always down here. They could swap places. Could be in either position. But what you have to remember, across from the 30-degree angle is a 1. The side opposite of 30 is 1. The side opposite the 60 is radical 3. And the side opposite the 90 is 2. Now again, I could go through and find a similar triangle again, just like we did before, right? Divide them all by 2. But you see that it's going to work just like the 45, 45, 90. So I'm not going to go through that and take time to do it. This is my special right triangle that you have to memorize. Across from the 30 is 1. Across from the 60 is radical 3. Across from the 90 is 2. Okay, so here are our examples. We're asked to find sine of 120 degrees. Okay, so I've got to figure out, well, what kind of rotation is that for 120 degrees? So this is my initial side. This would be a 90-degree rotation. This would be 180. So 120 degrees is between them. Okay, now here's where I talked about how you've got to think through what we did before. So if I rotated from here to here, that was 90. So how much more did I have to rotate to get 120? This rotation is an extra 30 degrees. Does everybody follow that? To give me 120 total. You're just awfully quiet. Y'all make me nervous. That's a 30-degree extra rotation. So now what is my central angle? 60. Because I have to make it all the way back to the x-axis. So that means the central angle is a 60-degree angle. Does everybody see how I think through that? So if that's the 60-degree angle, then this one up here is going to be my 30-degree angle. Across from the 30 is a 1. Across from the 60 is a radical 3. Across from the 90 is a 2. Now, I am in the second quadrant. All students take calculus. Only sine is positive. Well, that's what I'm asked to find is sine, so I know my answer is positive. Sine is the opposite over the hypotenuse. So I'm from here. I'm from my central angle of 60. The opposite is radical 3. The hypotenuse is 2. So sine of 120 is radical 3 over 2. Any questions? Next is cosine of negative 300. So again, if I was rotating this one, I know negative 360 brings me all the way back here. So I'm not quite to negative 360. I'm just to negative 300, so I know I'm in the first quadrant. Now, if I rotated negative 300, think about it. Rotating all the way to here is negative 270. So how much more did I have to rotate to get to 300? I had to rotate 30 more to get to 300. So what is my interior angle? 60. So that's my 60-degree angle, which means the other one is 30. Across from the 30 is 1. Across from the 60 is radical 3. Across from the 90 is 2. I'm in the first quadrant. I know all trig functions are positive in the first quadrant. Okay, now I'm asked to find the cosine of my central angle, which is 60. Cosine is the adjacent 1 over the hypotenuse 2. So cosine of negative 300 is 1/2. Okay, next we're going to find sine of negative 4 pi over 3. So because it's negative, I know I'm rotating clockwise, okay? And I'm dividing it into thirds. So this would be negative 1 pi over 3, negative 2 pi over 3, negative 3 pi over 3, or negative pi puts me here. Now negative 4 pi over 3 is going to put me here in the second quadrant. So now I know pi over 3 is 60 degrees. That's one that you need to have memorized. So if I rotated here, that was negative 3 pi over 3. So to rotate to here, that's an extra pi over 3, which means I rotated an extra 60 degrees. So what is my central angle? It's 60, because this time it's the same thing that I rotated by. Right? So that means this is a 60-degree angle, which means the other one is 30. Across from the 30 is 1. Across from the 60 is radical 3. Across from the 90 is 2. I'm in the second quadrant, so sine is positive. It's the only thing positive, so my answer is positive. Sine is the opposite over the hypotenuse. My opposite angle is radical 3. Sorry, my opposite side from the angle is radical 3. My hypotenuse is 2. So sine of negative 4 pi over 3 is radical 3 over 2. Okay, and then the last one here is cosine of 7 pi over 3. So I know 6 pi over 3 is a full revolution. That would be 2 pi. So 7 pi over 3 is just one more 60-degree revolution. So since 2 pi put me back here, or 6 pi over 3, then I rotated another pi over 3 to get here, which means my central angle is 60. Which means this one's 30. Across from the 30 is 1. Across from the 60 is radical 3. Across from the 90 is 2. I'm in the first quadrant, so all of my trig functions are positive. So I know cosine is positive. Cosine is the adjacent over the hypotenuse. So adjacent to my central angle is 1. And the hypotenuse is 2, so cosine would be 1/2.